Well, students, in the last class, we have defined the notion of divided differences, and we have also derived a formula for divided differences for a given set of data generated from a function. In this, we would have observed that the formula is not well defined if two or more nodes are repeated, right? But often we want to deal with divided differences with repeated nodes. Well, in the construction of interpolation, such a situation will never occur. However, when we are dealing with the error analysis of quadrature formulas, that is numerical integration formulas, that time we need to handle the divided differences with repeated nodes. Therefore, we have to think how we can give a definition of divided differences which makes sense even if the nodes are repeated, and that definition should coincide with our classical definition defined in the last class when all the nodes are distinct. That is the aim of our lecture now. In this lecture, we will try to derive an equivalent definition for divided differences, which makes sense even if the nodes are repeated. Let us first recall the definition that we have given in the last class for an nth order divided difference. The nth order divided difference of a function f at the nodes x0, x1 up to xn is denoted by this, and it is given in terms of the lower order divided differences, and the formula is given by this. You can see that if xn is equal to x0, say, then the denominator becomes 0, and therefore this formula seems to be not well defined, right? That is the main problem for us to go ahead with this formula when two or more nodes are repeated. Well, at this level, we have a question. Do we face this problem only when xn is equal to x0, or do we face this problem when any xi is equal to xj for any ij in the set 1, 2 up to n, right? So if ij are any index coming from this set, and if we find that xi is equal to xj, then also do we face this problem? Well, the answer is yes. It may not be apparent from the formula. Say, for instance, let us take, say, x1, x0, x1, x2, x3. Its formula is given by f of x1, x2, x3 minus f of x0, x1, x2, right, divided by x3 minus x0, right? If x3 equal to x0, it is very clear that this formula has problem. What if x1 is equal to x2? Then it looks like this formula takes the form x1, x2 is now x1, x3, and therefore you have f of x1, x1, x3 minus f of x0, x1, x1 divided by x3 minus x0, right? Assume that x3 is not equal to x1 and x1 is not equal to x0. It may look as if this formula is fine in such a situation, but it is not true, because we have learned that divided difference is symmetric with respect to permutations. Therefore, I can as well write this as x0, x1, x1, x3 as f of, I will just push this to the first place and this to the last place and bring these two guys to this place. So I'm just permuting these nodes. By permutation, the value of the divided difference will never change. That is what we have learned in the name of symmetric property. Therefore, this should be equal to x1, x0, x3, x1. And now if you apply this formula to this divided difference, we will have f of x0, x3, x1 minus f of x1, x0, x3, right, divided by x1 minus x1, and that seems to be a problem. This can also be viewed from the divided difference table. You see, any higher order divided difference is going to depend on the lower order divided differences in a very strong way. If any one of the lower order divided difference is not well defined, that will eventually affect the higher order divided differences also, right? So that is what is happening here. Okay, at this level, you may see as if there is no problem in calculating this term using this formula, but actually it has problem with the lower order divided differences if any two nodes got repeated. Okay, and using symmetric property, it is very clearly seen in the formula of the nth order divided difference itself. Therefore, it is not very clear, can we accept this as a definition of the nth order divided difference when two or more nodes are repeated? Well, as I said, this situation will never occur when we are working with interpolations, right? But we need to settle this problem before going to do the error analysis for quadrature formulas, because there we will come across situations where we have to handle the divided differences with repeated roots. So what to do in such situations? Well, we will look for an equivalent definition of the divided difference, which is still valid when the nodes are repeated. What is meant by equivalent definition? We have one definition, we want another definition which will coincide with our original definition if the nodes are distinct, and that new definition should make sense even if the nodes are repeated. That is what we want ultimately, and Hermite-Genocchi formula precisely gives us such an equivalent definition. So let us now state and prove the Hermite-Genocchi formula. To establish the formula, basically we need to assume that the nodes are distinct. So we will assume this condition and derive the formula. Once we have the formula in hand, we will observe it carefully and see that, well, it can be applied to the situations where the nodes are repeated. And therefore, we will go ahead and take that formula and apply in such general situations also. That is the overall philosophy of this theorem. To establish this formula, basically we need to assume the condition that the nodes are distinct. F should be n times continuously differentiable on the interval in which we are interested in. Then the Hermite-Genocchi formula says that your divided difference with nodes x0, x1 up to xn for the function f can also be written using this formula. You can see that this is a multiple integral over a set which is denoted by tau n, and the set tau n is given by this expression. We will have to first understand how this set looks like. For that, let us just take n is equal to 1. You see, tau 1 is equal to the set of all t1 such that t1 is greater than or equal to 0, I equal to 1, right? Then this summation is just one term, t1 is less than or equal to 1, right? That is precisely your closed interval 0, 1. Now let us take n is equal to 2 and see how this tau 2 looks like. Tau 2 is equal to the set of all tuples T1, T2 such that both T1 and T2 are greater than or equal to 0 and their sum T1 plus T2 is less than or equal to 1. Let us see how this set looks like in R2. See, both T1 and T2 are non-negative, right? So therefore, the set tau 2 sits in the first quadrant as far as the lower bound is concerned, right? This area. Now coming to the upper bound, and the upper bound says that T1 plus T2 should be less than or equal to 1. What it means, when T1 equal to 0, then T2 should be 1. And when T2 is 0, then T1 should be 1, right? In between, they should be in such a way that their sum is less than or equal to 1, right? So you can write T2 as less than or equal to 1 minus T1, and that will define you this set which is bounded by these 3 lines, right? And not only that, you also have one extra condition that T0, which is sitting here, is given by 1 minus sigma equal to 1 to n Ti. Okay. So you are going to integrate the nth order derivative of f evaluated at this point. And then you take the integral over this set, okay, if it is R2, and similarly for higher dimensions, the set goes in a similar way, right? And now you have to show that this complicated formula is actually equal to this. What is this? This is nothing but f of x1 to xn, very simple to understand, but the other side is little difficult. x0 to xn minus 1 divided by xn minus x0. Okay, so this is elementary to understand it, but this is little bit difficult. This is also elementary. Now, how to show this is the question. The proof of the theorem is by induction. As a first step, we will prove the formula for n is equal to 1. And in this case, as we discussed, tau 1 is the interval 0 to 1. And we further use the expression T0 is equal to 1 minus T1. Let us see how the right-hand side formula will look like when n is equal to 1. We will put n is equal to 1 and T0 is equal to 1 minus T1, right? And tau n, which is tau 1, equal to 0 to 1, closed interval. And therefore, the right-hand side can be written as 0 to 1 f dash of T0 x0 plus T1 x1 dt1. And now we will put T0 equal to 1 minus T1. And that gives 0 to 1 f dash of 1 minus T1 x0 plus T1 x1 dt1, right? And that is equal to 0 to 1 f dash of x0 plus T1 into x1 minus x0 dt1. Now you see, we will integrate this with respect to T1. We will get f of x0 plus T1 into x1 minus x0 divided by x1 minus x0, and the integration is over 0 to 1, right? And that gives us f of x1 minus f of x0 divided by x1 minus x0, and that is nothing but the divided difference of f at the node points x0 and x1, right? When x1 and x0 are distinct, this step makes perfectly meaningful, and that leads to our classical definition of the divided difference of order 1, and we started from the proposed Hermite-Genocchi formula with n equal to 1 and showed that that is nothing but the first order divided difference. Therefore, the result is true for n equal to 1, and as the next step, we will assume that the formula holds for any k greater than or equal to 1 and prove the formula for k plus 1. Let us see how to do this. Since we have to prove the formula for n is equal to k plus 1, we will take the right hand side and put n equal to k plus 1 on the right hand side of the Hermite-Genocchi formula, and we get this. Now we have to show that this is equal to the classical definition of divided difference of order k plus 1 for the function f, right? That is to show that this entire thing is equal to f of x1 to xk plus 1 minus f of x0 to xk divided by xk plus 1 minus x0. Let us see how to prove this. Note that we have T0 is equal to 1 minus T1 plus T2 plus up to Tk plus 1, right? So substitute this in the place of T0 in the expression. Then we will have the argument of fk plus 1 as x0 plus T1 into x1 minus x0 plus dash 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 up to Tk plus 1 of xk plus 1 minus x0, right? I'm just putting T0 equal to this expression. Therefore, I will just substitute this expression with this argument of fk plus 1. And then what I will do is I will separate this and bring one component of this set separately and integrate this entire thing for that variable. So I will bring out the integration for tk plus 1 separately. So I have taken fk plus 1 as it is, and this expression I have rewritten like this by putting T0 equal to 1 minus T1 plus T2 up to Tk plus 1. And now what I did is this Tk plus 1 alone I took and integrating over 0 to 1 minus T1 plus T2 up to Tk. So how I'm getting this? Because that is how the set tau k plus 1 is defined. If you recall, it is nothing but the set of all T1 to Tk plus 1 such that all Ti's are greater than or equal to 0, I equal to 1, 2 up to k plus 1. And not only that, this part, sigma I equal to 1 to k plus 1, Ti is less than or equal to 1, right? Therefore, the variable Tk plus 1 varies from 0 to Tk plus 1 is less than or equal to 1 minus T1 plus up to tk, right? That is what I have put as the limit to this integral. When I'm integrating with respect to tk plus 1, I'm taking the integral from 0 to this point, right? And all the other components of the set tau k are clubbed together and kept outside. Let us do this integration later. Therefore, I have also moved dt1 to dtk outside the bracket. Let us integrate this explicitly. So when you integrate this, you can see that the integrand is the k plus 1th derivative. Therefore, one derivative will get reduced here. And the integration is with respect to tk plus 1, right? Therefore, we will have this integration as, see, this outside integral I kept as it is. I'm only performing the integration inside this bracket. So since we are integrating fk plus 1, therefore one derivative became less here, and this argument is as it is sitting here. And since the integration is with respect to k plus 1, we have its scalar multiple xk plus 1 minus x naught is sitting in the denominator. And then we are taking the limit tk plus 1 equal to 0 to 1 minus t1 plus t2 plus up to tk, right? And then outside we have dt1 up to dtk. So this is a very simple 1D integration. Now let us put these limits into this expression and rewrite it. We will get the left-hand side is our Genocchi formula, and the right-hand side you can see that I'm taking this integral inside and putting the upper limit. I'm getting integral tau k, this is the upper limit, minus integral over tau k, lower limit, and I'm having 1 by xk plus 1 minus x naught, which I took outside, right? So this is just putting the limits and then integrating term by term. Now you can see that by our induction hypothesis, we assumed that the Hermite-Genocchi formula holds for n equal to k, right? Therefore, this is precisely the Hermite-Genocchi formula for n equal to k, you can see here, as well as we are integrating with respect to tau k, and it is over dt1, dt2 up to dtk, right? So as per Genocchi formula, this should be equal to the kth order divided difference of f at the node points x0, x1 up to xk. There is no ambiguity in this. Now this is also precisely the Genocchi formula with n is equal to k. But only thing is the argument looks little different. If you have this, it's very clear that we will write x0, x1 up to xk as the nodes, but we have different argument here. But you can clearly see that x0 here is replaced by xk plus 1, right? Of course, here also we should rewrite this argument as t0 x0 plus t1 x1 plus up to tk xk, where t0 is 1 minus t1 minus t2 up to minus tk. That is how we take, right? That is why this entire thing became the kth order divided difference as per the Genocchi formula. Similarly, here this entire argument can be written as t0 into xk plus 1 plus t1 x1 plus up to tk xk, right? Wherever x0 comes in our original Genocchi formula, we are just putting xk plus 1, that's all, right? Therefore, this entire first term as per the Genocchi's formula, since we have assumed that it is true for n equal to k, will become f of xk plus 1. Instead of x naught, we have to put this, and all the other nodes will remain as they are, xk. So there are k plus 1 nodes, therefore it's a divided difference of order k. But I have written this like f of x1, x2 up to xk, xk plus 1. But actually, as per Genocchi formula, it should be like this. Why I'm writing here a different form? Well, that is not very difficult to see because the divided difference of f is actually symmetric, right? Therefore, I can always write this, which Genocchi formula gave, as this because of the symmetry of the divided difference. And that is precisely the classical definition of the divided difference of f at the nodes x0, x1 up to xk plus 1, right? So this proves the Genocchi formula for k plus 1, right? That is, assuming k, we proved for k plus 1, and we already proved for n is equal to 1. Therefore, by induction, we can conclude that the Genocchi formula is true for any n, and this completes the proof. The following result is a direct consequence of the Hermite-Genocchi formula. Assume that you have n plus 1 nodes in the interval a comma b. Now that we are relaxing the condition that they are distinct and saying that they are not necessarily distinct. And further, we have f, which is n times continuously differentiable on the interval ab. Then you can see that the function x0, x1 up to xn going to the corresponding divided difference of order n is a continuous function on Rn plus 1. Okay, so you are just considering this as a function of the n plus 1 tuple like this, which is an element in Rn plus 1. And we can conclude that this is a continuous function. And further, what you do is, for any x, you take this vector x0, x1 up to xn. Not necessarily all are distinct, but this vector tends to this vector where all the components are equal and equal to x. And now you are taking the limit in this function. So this limit exists. That's what is the conclusion. And this limit is the nth order divided difference given like this, where x is repeated n plus 1 times. And most importantly, that is given now by this formula. That is f of x, x up to x, n plus 1 times repeated, is nothing but the nth derivative of f at x divided by n factorial. Well, the proof of the continuity is outside the scope of our course, then therefore we will omit it. And the proof of the second part follows immediately from this elementary formula. I leave this as an important exercise to complete the proof. Well, you can assume this fact, which is an exercise in the volume integrals, and so it is a part of your multivariable calculus course.